Hello everyone. Greetings to you from the PG and Research Department of Chemistry, Bishop Heber College, Trichy. I'm Assistant Professor Lydia and I'm here to present a lecture on kinetic theory of gases. It is a set of empirical generalizations put forth by Clausius and Maxwell to explain the behavior of ideal gases. Have you ever changed an old incandescent light bulb? You might have noticed what looks like a black powder coating on the inside of the bulb. That black coating is actually metal atoms of tungsten that have escaped from the tungsten filament of the bulb, and it has condensed on the glass surface. And it was Langmuir who was first able to solve this problem because he was familiar with KMT, the kinetic molecular theory. Among the different states of matter, the gaseous state are the most simple. Their uniformity is one of the reasons for that, and there are many well-known laws of gases. A few to be mentioned are Boyles Law, Charles Law, Graham's Law, Dalton's, and that of Amadeo Avogadro. However, in the 19th century, there were a few people who were able to give sound theoretical basis for these laws, and they were Chronic, Clausius, Maxwell, and Boltzmann. The picture of Clausius can be seen in the slide. It is essential that we have a good understanding of some laws as well as basic terms that are helpful to study gaseous systems. The first term that we are going to study is pressure. Pressure is defined as the force exerted by the impacts of the molecules of gas per unit surface area. The system A international unit of pressure is Pascal, the symbol being PA with a capital P. There are also other units like torr, millimeter mercury, and atm, that is atmosphere. As we can see, they are all interconvertible. The next term is temperature. Temperature is the degree of hotness or coldness of a gas. Temperature in general refers to the energy of a system, and it is useful in determining the average kinetic energy of a gas. Temperature is commonly measured in degrees Celsius. However, in the following derivations we are going to study today, temperature is mentioned in the Kelvin. Centigrade scale is divided into 100 divisions based on the freezing point and boiling point of water, and Kelvin scale, which has the range from 273 to 373, equals 0 to 100 degree centigrade respectively. Kelvin scale is represented as the absolute scale because it has no negative value. An absolute scale refers to Kelvin scale, and 0 Kelvin is represented as absolute zero because theoretically speaking, the volume of any gas at absolute temperature becomes zero. So in actual representation, we can say that a gas becomes converted completely into solid or liquid before absolute zero is attained. Now we may move on to the different laws that explain the nature of gaseous systems. The first law is Boyles Law. According to Boyles Law, the volume of a given sample of gas is inversely related to its pressure when the temperature is constant. You can see the mathematical expression. We can observe on the graphical representation, the plot between P and 1 by V gives us a straight line. The illustration shows Boyles Law. When temperature is constant, we can see that pressure and volume are inversely related. We are moving on to Charles' Law. According to Charles' Law, the volume of a given sample of gas is directly related to Kelvin or absolute temperature when the pressure of the system is constant. Already we have seen what it is meant by absolute zero or absolute temperature. We can see the mathematical expression. This is the graphical representation of Charles' Law, and volume, when it is extrapolated to 0 Kelvin, the temperature is 0. You can see that theoretically the volume of the gas has become 0 too. This is the illustration showing Charles' Law, where pressure is considered to be constant, and we can see with increasing temperature there is increase in the volume of the particular gas. The third law we are going to see is about Avogadro's law. Equal volumes of all gases at same pressure and temperature contain equal number of molecules or moles. The mathematical expression says V is directly proportional to N, that is the number of moles, and removing the proportionality sign we are introducing another constant which is called Avogadro's number. The value is 6.023 into 10 power 23, and this is the constant of proportionality here in this case of Avogadro's law. And for two gases we have N1 is equal to N2, also V1 is equal to V2, provided that temperature and pressure are constant. This is an illustration showing the relationship between the number of moles and volume of a gas, that is Avogadro's law. We can see the proportional increase in the volume in relation with the increase in the number of moles of the gas that is present in the closed system. Avogadro law has application in our real life. Every day we have Avogadro law in action. For example, pumping of air into football increases the number of moles of a gas and therefore its volume. We know without air how shrinked a ball is, and when we inflate it with air, the volume naturally becomes increased. Same is the case when we breathe. We know how our lungs become expanded when we breathe in, and when we breathe out, we expel the air from the system, resulting in reduced volume of the lungs. And another classical example is balloons that are filled with air and helium. This is an illustration showing the relationship between volume and pressure. As we have already seen, greater the volume, lower will be the pressure, lesser the volume, higher will be the pressure. And the thing that has to be considered constant is the number of moles. And combining all these equations, we can arrive at the combined gas laws, or it is also sometimes referred to as ideal gas equation. The statement of combined gas laws is the simultaneous effect of change of pressure and temperature of a gas can be studied by combining Boyles law and Charles' law, and the derived equation is called